Welcome to one and all present here. My name is Jesse, and let's start this amazing journey of physics with the first movie called Units and Dimensions. Well, although this is a very small chapter, as you know, well, there are a lot of things which can be asked from these. The questions here are not very hard. It's quite easier as compared to all the chapters. Just a little bit of effort is required to put on. So before that, let me give you a small recap of what this is about, right? So I'm planning to do it as small recaps for each and every chapter. Then we'll solve a bunch of questions so that you might understand what it is about, right? So in this chapter, units and dimensions, although this seems like a new chapter, especially you'll get to know, you'll be familiarized with all the new terms of what are all the words in physics, whatever it may be. It may be related with any field, electromagnetism, optics, modern physics, whatever. And so, in a brief, if you look at it, units and dimension, it has like two parts. First one is about units. The second one, dimensions. And the third part is error, errors, error analysis. Then we have the fourth part as instruments that we'll be using. It's nothing but vernier caliper and screw gauge. I hope till this is clear. This is the basic outline of the chapter. This is what is there in this chapter, right? If you ask. So what do we study in units? We study about number one of the all the units which are there, the seven fundamental units. Then we have units for each and every physical quantity. And then we have one formula, N1 U1 equals N2 U2. Conversion of units. Right. This is what we do in units. What about dimensions? Writing dimensional formula. Then let's say for such a physical quantity which is given, how do you express dimensional formula in terms of basic dimensional formula of L, M, L, and T? Let's say it's X, Y, and Z. I'll explain each and everything later. This is just a brief of what we are all going to study. And then uh, even in dimensions to derive dimensional formula, which will actually come here, right? That's what is there in dimensions. And know about quantities which have or have not dimensional qualities, dimensions. For example, let's say have nots is nothing but angles, trig function, exponential, and so forth. Even sine functions, which will come under trigonometric functions. Then in error analysis, we have types of errors. Like we have random error, personal error. Let me just list a few. Random. Then we have um various other types, not able to recollect, but maybe instrument, instrumental, so forth. Well, if I remember, I'll just definitely write it. We have types of errors plus correction. Yeah, and also I would say to add another one column. This is for rules of significant figures, sig figs plus rounding off, which I forgot. So, so there are certain rules for to count how many significant figures are there, how to round off certain things based upon uh, the operation which is given. Plus minus will follow one rule, multiply and divide will follow one rule. This is least number of sig figs, least decimal places. Where you get this is completely combined with the concepts of accuracy plus precision. Accuracy is nothing but closeness to the value. Precision is nothing but, it's like, to give you an example, you have a dartboard. Let me take a dartboard. Let's say you have a board like this. Let's color it some white. Fill it here. Give it a border. Right. So this is like the dartboard. What I'm going to do is just paste it again. Okay. So let's keep black arrow here. So this is the bullseye. Let's say two people, person A, which is this, hits it somewhere here, maybe somewhere here. B hits it here, 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 here. This is person B. Precision is nothing but number of times you hit. Well, this is represented by the decimal points. This is nothing but the closeness to the value. So if you see here, in this case, I'll take another color to differentiate. Person A, if we talk about person A, this person has hit only two times over here. But are they accurate? Accurate enough? So, because look at the distance, it's very, very less, right? Similarly, if you take person B, so person A is accurate, but is he precise or not? But well, there are only two. And look at B, how many times B has put. So maybe precision wise is less. But look at B. Precision wise is more, but accuracy is okay. Maybe these two are there. But what about this? What about, okay, even let's say these two also count. What about this one? Or maybe just to differentiate, let me put these two right here. Just a minute. So that it'll be easy. to differentiate. Why it's not selecting? Okay, fine. I'll put it somewhere there just to differentiate. Yeah, or this is better. Right. So this is precise somewhat, but not accurate enough to get to this bullseye. So accuracy is down. So this is what is about the concept of accuracy and precision. Slowly up, when we do problems, you'll understand types of errors. Then you also have these. 1 minute, let me change color. Yeah, you also have average error, mean errors, and all that. Average, mean, absolute, relative, plus percentage error. Percentage error is nothing. Relative error into 1000 into 100 percentage will give you percentage error. And finally, we have vernier caliper and screw gauge. This is also very, very important. A lot of questions also come from this. Nothing is there in this, only least count part, the MSD and VSD in vernier caliper. Screw gauge, you have it as pitch, circular scale divisions, and so forth, which are the terms which are going to come up. So this is the complete analysis of units and dimensions, right? All right. So now moving on to what's there in the chapter. Let's take a just a quick brush up before we touch up with the questions. Right. So as we were talking, this is our full skeleton of the chapter, and I'm just going to explain it off. Units is nothing but like units is of a physical quantity, right? Physical quantity is nothing but which can be measured, which can be seen, which can be expressed or measured, like wherein the laws of physics satisfy. That is the meaning of physical quantities, and these physical quantities are measured by something called units. It's like you've studied in chemistry that atoms are the basic building blocks. Although after that there are subatomic particles. We'll just taking on to the Dalton theory, like atoms are building blocks, just like bricks are building blocks of a home. Similarly, units are the building blocks of physical quantity, right? It's like a known fixed physical quantity, right? So let's take a physical quantity. Maybe we can just take this line, for instance. Let's say I give the name of this line as two, not centimeter. Well, let me just take anything, two bricks. Notice how I've constructed this thing. This is a physical quantity which I have designed obviously because this is not two bricks as we know this should be something in like length, right? Because it's a line. But let me just give you an understanding. This is a very, very imaginary thing. Two bricks. How is this constructed? There's this number two which signifies something. Bricks signify something, right? Let's take this physical quantity. Let's name this physical quantity as Q. So Q is nothing made up of N, which is, let's say, the number, and bricks, which is nothing but the unit, which is there, which we take it as U, right? So it's like a small formula. Q equals NU, where N represents the number and U is nothing but the unit. So here unit can stand for anything, but over here as its length, it's nothing but it should be something like meter, centimeter, kilometer, and so forth. Why I explained this Q equals NU? This is like, the address of a physical quantity, because this will be used in this N1U1 equals N2U2 conversion of units. Or there are also easier way to do it. I'll just explain you when it comes in problems. And seven fundamental units which are there, which is nothing but for, write it in red. And also before that, units are of two types: fundamental, which means that these are the basic building blocks, and then derived ones, which means that from these fundamentals you can make these up, right? So let me just give you an example. Fundamental is nothing but length, mass, time, temperature, and so forth. And actually there are seven fundamental units and rest all will come here. So what are those seven fundamental units? They are nothing but, you can actually make a table: physical quantity, then you have its unit, then you have symbol. This for a easy understanding which I made. First is length, unit is meter, symbol n. Mass, kg, symbol kg. Or let me write it as kilogram. That will be right. Then time we have, it's about seconds. And we usually follow this system of SI, System de International. It's pronounced in French, but there are also other systems like MKS, which stands for uh, meter, kilogram, second. Then we have CGS, centimeter, gram, second. FPS, force. Oh, sorry, not force. It's actually foot. Pound, unit of mass, and second. Then also, yeah, that's it. These are the systems that we have, I think, for our. So these are just the systems. Just make a note of it. Let me just highlight it in a good color. That it's easy. Okay. These are just the systems that we use. Okay. So let's go back. And then we have temperature. 1 minute. Sorry. Changed. Okay. Kelvin. K. Seconds is S. Right. Current. Electric current actually. We have ampere. A. Luminous intensity, which is nothing but candela. CD. It's nothing but how much light is focused upon something. Quantity of matter. We usually represent in moles. And these are just 3, 6, and 7. Also, these are fundamental units. Also, add supplementary also, making it total to a 9. What are the supplementary units? It's nothing but solid angle and plane angle. Plane angle is nothing but angles that we use for arcs. This the theta that we use. This is, or actually, and also Kelvin is represented also as theta. Sometimes I'll write it here. I'm sorry. So be careful in questions. Very, very important because even I have made mistakes as not distinguishing both. Solid angle, okay, let's write for plane angle first. Plane angle is for radian. Simple as rad. We know how much 57 point some degrees is nothing but 1 radian. Even there's also gradient system where 1 radian is nothing like, to just give you a just an example, to just show you what 1 radian is. It's like you divide a circle into 360 parts, is what a radian is about. But in a gradient system, you divide the circle into 100 parts. This is for gradient system, right? What about solid angle? It's the unit is steradian. It's like radian, but just with the S of the solid. And SR is the short form, steradian. It's like for a 3D space, you need to measure an angle. It's a bit hard to draw. Just bear with my drawing. Let's take, okay, something like this. This whole part. How do I really highlight? I really don't know. Okay, maybe this part. Okay, let me lighten it up a bit so that it's very, very easy for to see. This is steradian, right? This is about radian and steradian. These are fundamentals. These are supplementary. Together, they constitute the basic building blocks. What about the derived ones? Derived ones are nothing but which come from the fundamentals. Like these, you'd be using as bricks just to, build the home. And for that, you have a lot of other uh, quantities to be said. Also, just one small thing which I noticed. Okay, let me get good color like brown. Yeah, there are formulas for these for solid angle and plane angle. Plane angle, you know the formula. L is nothing but R by theta. So, no, sorry. Theta equals L by. This formula you will use in a lot. You can easily write this as L equals R into theta. And this also forms the basis for what is that called? A circular, not circular motion, system of particles in rotation, where it's nothing but this is like the linear quantity. This is the angular quantity. Is nothing but R into angular quantity or angular part. Similarly, you can write what is the linear part? Maybe we'll write velocity. R into what is the angular part? Angular velocity. What is angular velocity? This is nothing but that omega that we see. Well, in chapters of SHM and waves, you get it as 2 pi by t, which will slowly come with the ladder. Surely come up with the ladder. Or let's give another example of acceleration. Acceleration is nothing but r into some angular part of acceleration. Let's call it angular acceleration, alpha. This is actually nothing but theta by t. This is theta by t square and so forth. As we will see, this is also very important so that you can derive the physical quantity. You can derive its dimension, the value of, let's say in a question they ask you to derive angular acceleration, the dimensional formula of angular acceleration, or the dimensional formula of angular velocity. It's easy. You know about linear velocity. Well, now I'll derive some very, very important physical quantities. Then we'll go up. And there are certain easy things that you can remember as a ladder, so that it's very, very useful. For example, let's start with the basic terms like length. We saw it's nothing but L. We usually put this bracket, it's like a square bracket that we put, right? And these are its symbols. Okay, okay, I didn't write the symbol over here. Okay, so length is L like this, mass is M, time is T, temperature we give it as K or theta, current is ampere, so A, luminous intensity we give it as I because L is already taken, or I think we give it as candle. I think, I'm not sure. Let me refer. And the quantity of matter, we'll just give it as mole. So very, very simple yet important, which are asked in exams, are nothing but length. Then we have time, which is nothing but T. Then mass is nothing but M. Then we have velocity. Let me just write. Velocity is nothing but LT power minus 1. What is velocity? The purpose of doing this is nothing but to make you derive all the uh, derived quantities very, very easily, so that there is no stress or fear to memorize all these dimensions. And as you do, keep practicing each and every derivation of these dimensions, you will get to know some of uh, the dimensional formula. For example, I know about velocity, acceleration, force, um, energy, and so forth, because I keep practicing those, right? And with practice, even you can also achieve it, because these are very, very important for building other buildings. Like a brick builds maybe the basement, then you need another set of for the first floor or the second floor. You build that and keep it in the side. Then when you join each and everything, you get a beautiful home. So similarly, like that, even these also, as you slowly progress, you'll eventually memorize them. Like you can just easily by heart it and you can write it down. So without wasting further time, how did I do velocity? Is nothing but length by time, which is nothing but distance by time. What is the formula of velocity or speed? Or even speed can be written using this. Velocity or speed. It's nothing but distance by time. What is distance? Distance is nothing but length family here. What is time? Time. And you need to know about certain families that I'll be introducing, like length family or energy family and so forth. What about acceleration? Acceleration is nothing but velocity by time. So what is velocity? LT power minus 1. What is time? Time t. So what do? You bring this above. This is how you write a dimensional formula. Then you bring it above. So LT power minus 1. And as you know the rules of exponents of when you bring something to the above, change the sign and write that sign of the exponent which is there will be changed. So minus 1 t power minus 1. And you know, when you multiply two exponential, you can just simply add them up. So t minus 1 plus minus 1, nothing but minus 2, lt power minus 2 for acceleration. What about force? Is nothing but mass into acceleration, as you might have studied in 9th or 10th. And so for these, mass is m, acceleration we have already derived, so we'll just write it as mlt power minus 2. We're just multiplying it, so no problem. What about momentum? If you recall the formula of momentum, momentum is nothing but mass into velocity, which is nothing but mass m into velocity is nothing but lt power minus 1. So m lt power minus 1 is for momentum. What about pressure? Pressure is nothing but force or thrust given by unit area. What is force? Actually, it is perpendicular force. This is very, very important as we'll be using it in the later chapters. Force is nothing but mlt power minus 2. And to say force, momentum, velocity, acceleration, these are very, very important. So I would suggest to, note down these four, since they can be used in a lot of ways. Like for pressure, we need the dimension formula of force. So will you keep deriving force F equals ma and then you keep substituting here? No. We can just remember it as mlt power minus 2, right? That is for pressure divided by area. What is the area? Area is nothing but the amount of space that something occupies. Let's say I have a square here of side A. What is the area of the square? It's nothing but A into A. What is A? Or you can take any area. Area is nothing but of length family, but it's nothing but length squared, because over here for a square or a circle or a triangle, the length is square. For example, squared. For example, a triangle, it's nothing but root 3 by 4 a square. So a is nothing but the length. Length is squared here. We really do not care about this part, the number part, the numerical part when we write dimensions. That is also a very important thing to be noted. For writing dimensions, we only concentrate on the quantities which are involved. So length family which is squared here. So area is nothing but L square. Even for a circle, it's nothing but pi r square. What is r? Radius. Radius is nothing but we measure it in length, meters or centimeters. So it's about the length family, and length family is getting squared here, L square. So that's why we write L square. So m L power 1, and when 2 goes up, change the sign and write. So 1 minus 2 t power minus 2. So 1 minus 2 is nothing but negative 1 ml t power minus 1 m L power minus 1 t power minus 2. It's nothing but pressure. Similarly, you will get that bulk Young's modulus, which is nothing but stress by strain and stress, have the same dimensions of that of pressure. Well, we discuss the chapter solids. I'll get into that, but before that, let me just give you you know, a whole chunk just for you to see what's there in each and every chapter. Because, for example, this will be useful, this will be useful, and so forth. Then we have a very important family, just like the length family that we saw. We have the energy family. Energy family consists of nothing but of members like energy, obviously, work done, heat treated as energy, heat energy. Even we write work done as nothing but pressure into volume, force into uh, distance. Yes, force into okay, force into distance. Right, that's for power. I'm sorry. These consist of the energy family. All these pressure into volume actually gives you work done if you check it out. Then we have force into distance. Oh, what? And all types of energies, whether it may be internal energy, whether it may be any form of heat, even sometimes nuclear energy. Wherever you see the word heat, energy, immediately remember this dimension m l square t power minus 2. Very, very important. And how did I derive this? Very, very simple. What is work done? Work done is nothing but even. Let's add kinetic energy, potential energy, mechanical energy, total energy, and so forth. Whatever energy it may be, whatever. Work done is nothing but force into some distance that you travel. What is distance? Nothing but length family. What is force? That's what we saw above. It's nothing but ml t power minus 2. Very important. As you slowly derive, you will get to know ml t power minus 2, right? So just multiplying these two. So m into L into L. Since both are there in the numerator, no need to worry. 1 plus 1 is 2. ml square t power minus 2. Very, very important. Because in competitive exams or like in 1 mark or 2 mark, you can easily score these. Let's say they give you a list of all some quantities and they ask you pick out the ones which have same dimensions or pick out the ones which have different dimensions. All these have same dimensions. So you just need to see if it belongs to the energy family or not. Similarly for others. It's like all forms of energy, work done, right? Then we also have other things like impulse. Okay, or what I'll do is certain things I will derive, certain things I'll just leave it over here so that you can work it out. For example, impulse. I'll tell you the formula. It's nothing but force into time. It's like, let's say with your fist you bang on a table. You have so much of force in your hand, but you have very, very less time. More force, less time. The impulse is very, very high. The amount of force which is transferred into the table, right? Impulse, and you have even in rotation, moment of inertia. Well, there's actually a table for that of where we compare the linear terms and the angular terms. But just to tell you what is moment of inertia is nothing but mass into radius squared. Radius is nothing but length family. So length squared. So it's nothing but ml square. So please do tell me what is impulse. How do you derive this? It's very, very simple, right? Similarly for uh, surface tension, nothing but force by length, which is nothing but ml t power minus 2 divided by length is L family. So LL can get cancelled here since they have the same power, m t power minus 2. What if I give you surface energy included here? Surface energy, what is that? It's energy, nothing but of energy. Oh, wait, no, I'm sorry. Surface energy is something different. Don't include it here. Sorry for that. Energy is nothing but energy by area, which is nothing but ml t power minus 2 ml square t power minus 2 divided by L square, which is nothing but mt power minus 2. This one quantity is a bit different. I'm sorry for writing it over there, my mistake. But this is very, very important. This is quite different from that what we have seen. Please do not include it in the energy family. Let's say an MCQ pops out and give the dimension of surface energy. And let's say you see ml square t power minus 2 over there, you hit the right answer. Click it as an answer or tick it as an answer. You're wrong. How did the surface energy come from? So it's very simple. Surface tension is nothing but force by length. Now what you do is you multiply length on numerator and denominator. Force into length is nothing but energy, we know. Length into length is nothing but area. And that's how this formula came. This is actually surface energy formula, right? Then we have uh, density, which is nothing but mass by volume. Please this, do derive this also, impulse. Then we'll slowly see of other things. Maybe time is nothing but 1 by frequency is nothing but 1 by uh, or I'll write it like this. 1 by, okay, f is nothing but time inverse. Let's say this is t equals 1 by f. So f is nothing but 1 by time. So what is time? 1 by t. So t comes on top, it's t inverse. And also there are two things that you need to see, two other dimensions. Very, very important, these two are. Because I don't know if you can, well, you can easily derive it, but I would rather say just by heart it for now, which is nothing but permittivity and permeability. Permittivity and permeability. Permittivity is nothing but epsilon naught. That's how you define it, mu naught. Actually, the definitions and what they actually represent for each of them is quite different, which I'll explain you when we slowly come into electrostatics, permittivity and permeability. Because permeable, permit is nothing but, let's say something comes or somebody comes to your home knocking on your door. Let's say if it's your friend, what would you do? You'll open the door happily. Oh, come in, you may say. Let's say a stranger who doesn't know you comes to the door, or maybe a lot of strangers come to your door. What do you do? And you might usually react to them as okay, first you ask who are they, and you don't immediately go and ask, do you really want to come inside my home? No, you don't do that because you don't know who are they and you don't know for what they came. And even if they tell you, can we come inside your home, you would say no because you don't know who you are. But let's say a friend that you know comes among them. So what do? So you allow the friend in, but you leave the strangers at the door because you don't know who they are until and unless the friend has some connection with them or the friend doesn't know them. So that is the meaning of permit and permeable, to allow something in, very, very specific, very, very selective, very, very choosy. But in this case, as we are talking about physics, it's not about people that we're going to select. It's about electric field lines or magnetic field lines that something or a material can allow inside it, permittivity and permeability, right? It's like the number of field lines which can be allowed. That is not actually the definition. The definition is quite a bit ulta for that. But just to give you what the dimensions are for it, for permeability, just remember this malt, MALT. You might have heard about malt, ragi that we use at home. Then you just remember this numbering. Just put 1, 2, 1, 2, plus minus, plus minus. Very, very important to say. What about permittivity? It's the same malt, MALT, but we put 1, 2, 3, 4 here. 1, 2, 3, 4. But this plus minus will just change as minus plus minus plus. This is very, very important, and you might get it. Let's say you need to derive the speed of light. Speed of light is nothing but speed family, right? Which means what? The speed of light has the same dimensions that of speed, of velocity, nothing but LT per minus 1. Speed of something. Actually, also in modern physics, there is a formula for it. C is nothing but 1 by mu naught into epsilon naught. And if you actually plug in the values of permittivity and permeability into this beautiful equation, you end up with this. Please do try and tell me, right? I'm sorry. Okay. Let's just put this in the side for now. Okay, let's come to the main certain points. Okay, that's for permeability and permittivity. Very, very important. That's why I wanted to tell you. Then we have a certain things which are non-dimensional, which are dimensionless. You have angles, uh, even numbers, constants like pi, e, so forth, right? Constants here refers to numerical constants, not constants in physics. For example, we have Planck's constant. This we easily derive from this formula called the beautiful formula E equals h nu. Very, very important formula also. Nu here stands for frequency. And we also have frequency, which is nothing but speed of light divided by lambda. That is also another formula of frequency. So hc by lambda, right? And how did this formula come? This formula is nothing but, what is speed? Speed is nothing but distance by time. But here we measure speed as speed of light. What is the distance that we are referring? We refer it as lambda. What is frequency? Frequency is what I told you here. Frequency is nothing but 1 by time. So why can't I write this, let's say, into 1? Because, there's no quantity. So this 1 by time, I can write it as frequency. So C by lambda equals frequency, and that is what is this formula that you'll get. So Hc by lambda, E equals Hc by lambda. And here H stands for Planck's constant. Similarly, there are a lot of other constants like gravitation constant, like F equals K Q by R square, or F equals GMM by R square. This is Coulomb's constant. This is gravitational constant. And each one has values. Also, although they are called, and since they are called as constants, which means they have a fixed value. And here constants, for which are dimensionless, are for numbers. Or these are numbers, numerical kind of. Then we have trig, log, etc., exponential, whatever. So all these are dimensionless. There are no dimensions for them. Let's say in a question it's asked, what is the dimension formula of solid angle, plane angle? You would say it's angle, which means it doesn't have a dimension. But very, very important, these two quantities have units. They have units, but no dimensions. Units, but no dimensions. Very, very important. Very, very important. They have units, but no dimensions. These are the only two quantities which are known, which satisfy this kind of, a condition. That is what is about dimension. And then you also have principle of homogeneity of dimensions. It's a very, very big and a vague term. Although it's not vague, it's very, like a complex, a stylish word. In layman language, is nothing but like onion rule, is what I would say. Onion rule is my term given to homogeneity of dimensions. What does this onion rule mean? Onion is nothing but onion plus onion, right? Similarly, it's like birds of same feather flock together, like a coat. So onion equals onion plus onion. Let's say you go to a supermarket, you pick up a tray, you get some onions. In that tray or cover, uh, as you would take from a supermarket, you only put the things of the same kind inside. It's not that you're gonna take one onion, you're gonna take one potato, you're gonna take one tomato, you're gonna take some beans, take some carrots, and so forth. Right? So you take quantity which is of the same kind. Similarly, if you really want to check, if you really want to find out if this physical quantity or the LHS or the RHS of certain physical quantities are equal, we use this rule. Onion equals onion plus onion. Like, let's say if the left hand side is of length family or energy family, the right hand side must be of length family and energy family respectively. Let me give you a small example. We'll just pick up an equation. I hope you have heard about this equation, lovely equation. V equals U plus A. You might have studied in ninth. There'll be one graph which is plotted, and the area for this graph. I think you would have remembered. And this is distance, and this is time here, and so forth. This is initial velocity. Then what you'll do is you'll find out the area by the trapezium method, and so forth. You'll get this beautiful equation. So how do I know if this satisfies this this LHS satisfies this RHS perfectly. For that, we use the onion rule. Onion equals onion plus onion. How many ever onions are there? First, we count. We treat each and every quantity like an onion. So let's see how many quantities are there here with the plus or the minus or multiplying, right? So this is one onion. This is one onion plus. So since just to give you a basic understanding of what this onion rule is about, and this rule is very helpful in the forthcoming cases. Onion equals onion plus onion. I'm just giving it in this form so that you can easily compare the equal to the plus and the plus. Then 80, this is also an onion. Although it's a very big onion, but still it's of the same kind. This is also an onion. U is also onion, 80 is also an onion. Now, what does V represent? V is nothing but the velocity. What is velocity? Whether it may be final velocity, initial velocity, middle velocity, or whatever name that you give, it's finally of a velocity family, yeah? Which means what? LT power minus 1. This is dimension. What about U? This is called as initial velocity. But what is it finally? It's a velocity, some kind of velocity. But anyways, in the velocity family, right? So we write it as LT power minus 1. But now let's come to this 80. This doesn't look like a velocity family. You might be wondering. Even I am wondering in the same way because it's not like of a velocity family of middle velocity or some velocity. So what do? Is we try to write 80 in terms of m, l, and t. So how do you write it? What is a? A is nothing but the acceleration. What is acceleration? Lt power minus 2 is nothing but a. What is t? Which is nothing but the time. Which means L t power minus 2 plus 1 since we are multiplying. So L t power minus 1. Hey, wow, we got it as L t power minus 1 plus L t power minus 1. Onion is onion plus onion. This is one onion, this is one onion, this is one onion. Yes, I can club all these together and put it in my basket. So this satisfies onion rule. Similarly, let's take another example. S equals ut plus half at square. What is this S? Distance. Distance, length family, L, yeah. Okay, this doesn't look like an onion, but let's simplify this to say whether if it looks like an onion or not. Express in form of M, L, and T. How do you do that? What is U? Initial velocity. What is velocity? Velocity family. So LT power minus 1. Into, there is a T, which is nothing but time. So T power minus 1, this get cancelled. Hey, wow, I got length. Nothing but length family. So this onion is satisfied. This onion is satisfied. But I just need to see this. Now, some of you might be wondering, hey, Jesse, should I also consider this 2 over here, this half over here? So is it that after I write my final dimension, should I divide everything by 2? No, no, no. Because what I told you, angles, numbers, constants, all these are dimensionless. So don't consider these while you're writing dimensions. Let's cut it with a scissor. We don't need this. So we only focus on this big term, 80 square. How do you write 80 square? What is A? Acceleration. Acceleration family, LT power minus 2. What is T? Time. Time is squared here. So T power minus 2 and T get cancelled. Hey, I got L. L equals L plus L. But don't confuse it as L plus L is nothing but 2L, right? Because we just seeing if the onions are satisfied. Onion equals onion plus onion. Or let's say there are 3 terms plus onion and so forth. And also, I'll give you another example, another thing to be pointed out. Let's say you have sine of We'll write a angle omega t plus phi. Here, in this case, maybe I'm not going to equate anything. Here, if you see omega t plus phi, we have this inside a sine function. What does it mean? It means that this whole quantity, which is sine here, should be dimensionless. As I told you, numbers, trigonometric log must be dimensionless. And so for that, this whole thing must be dimensionless. So which means that omega t plus phi must give you something which is dimensionless. So phi must be dimensionless and omega t must be dimensionless. This is nothing but onion rule. Onion equals onion plus onion plus onion. So how do you make omega t dimensionless? What is omega? As I actually told you, omega is nothing but 2 pi by t. And you will eventually know that this is also t. But what is this t? Time period. You'll know get to know about in the later classes. But t here refers to time period, nothing but time family. What is this t? T is nothing but the time that you have moved through the SHM as talking with the SHM and waves. Nothing but time family. Similarly, so which means that these two would get cancelled. And 2 pi. What is 2 pi? It's an angle. Angles do not have any dimension. Satisfied. Phi, which is nothing but phase angle. Phase angle. In the word phase angle, you have angle. Angle which has no dimension, which means is also dimensionless. So dimensionless plus dimensionless must give you dimensionless. So if they ask you a question, does this equation satisfy the rules of homogeneity? You would say yes, it does satisfy because you have verily proved this condition. Onion equals onion plus onion. If this is not proved, it's not homogeneous. And very, very important, if an equation is dimensionally correct, it may or may not be physically, or like when you experiment it out or when you plug in values, it may or may not be correct. But if it's dimensionally incorrect, it will never be physically correct. It will never be correct when you plug in the values. For example, I can write this s equals ut plus, instead of, I would take the half out and I can just write at square. It is dimensionally correct. But physically, when you substitute values of a, t, u, t, and s, you feel that there is some lagging between the LHS and RHS. It is because of this half. And this half is determined usually by experimental nature, or they determine it by deducing formulas of it. This half. You cannot get this half in dimension because obviously in dimensions we're only going to see the physical nature of just the building blocks. If the building blocks are same, well, add up everything and you can build the home. If it's not same, don't build. And so that is what is till dimensional formula and writing till there. Next part is about significant figures and rounding off. Well, we have only three more to go: significant figures and rounding off. That's number one, error analysis, number two, and finally, Wernicke caliper and screw gauge. Right? About significant figures, sig figs, as we call them. Significant figures, as is there in the name, it's very, very significant. Significant. It's very important, and usually it is used to give the accurate result for any experiment or any observation that you're doing. A physics experiment or something like that. So that's what they use it for. There are very, very simple rules for this, and even the questions are very, very easy to do. They just give you a big number with a lot of decimal places in it, and they'll just ask you to count the number of significant figures in it, or just find it out. So the rules are simple. Let's go with the rules. So the first rule is non-zero digit are counted as significant figures, right? I'll give you examples also at the end. First, we'll just go up with the rules. And zero between non-zero digits are counted as significant figures, right? Like, for example, for this example is 8.314, nothing but the value of universal gas constant actually. And number of significant figures that it has is that this is non-zero, 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 non-zero. So four non-zeros, so four significant figures. And for this, maybe we'll keep this 7.03 or change 305. For this zero between non-zero, 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 non-zero. This is zero, but between two non-zeros, 3 and 5, so you count it. So it's 4, right? Then we have this all zeros which are between non-zeros, and another condition which is but before a non-zero. Sorry, not between non-zeros, actually, uh, after decimal, actually. After decimal, but after decimal point, but before non-zeros. Don't count it as significant figures. Well, instead of this very, very big definition, let's call this as an orphan rule. Now I'll tell you how to apply it. It's a very, very easy rule. We just name it as orphan rule. So every time when we do problems, you can just, okay, you just need to apply the orphan rule, right? Now, next comes in this zeros at end are nothing but comedy pieces, which means don't count them. And also, let's say, and okay, we just keep it as end of decimal place. If let's say the number is non-decimal number and there are zeros at end, still don't count them. They're still comedy pieces, right? And also, if a number has a unit to it, let's say 13.3990000 centimeter, you are supposed to count each and every digit. Although you would feel that these three zeros are comedy pieces, you're supposed to count only for this case. And last one point is that let's say you have just a whole number like 23 or pi or e or 17, 22, etc. It has infinite amount of significant figures. Why? Because let's say you write the number 23, you write 23.0000 and so forth. And this is a very fixed number. So it has infinite amount of significant figures. I think you get till there. That's the significant figure part. Now we come to rounding off. Let's pick another color. Let's make life colorful. Right. So rounding off, just remember this kind of flow chart. So you want to rounding off at any places like 4 or 5 or 6. Rounding off is nothing but they'll just give you a number 1, 2, 3. Okay, let me just write a number 4.31507768. They ask you to round off till 4 decimal places, which means that this is first decimal, second decimal, third decimal, fourth decimal. So I need to remove this part. Let me cut it with the scissor. So for that, what you do is you look at this digit at the fifth decimal place, and then you decide what to do, right? So for that, let's see some rules. Rules are very simple for rounding off. If the digit to be rounded off is 5, what do you do? If the digit to be rounded off is not 5, what do you do? Not 5, there are two cases. One is greater than 5, one is less than 5. Here, if it's 5, what you do? You look at the left. You look at the left, right? And if you see a non-zero number, there is two cases over there. Yeah, let me write this non-zero over here because there are two cases over here. If you see a zero, just leave it at okay. A non-zero, there are still two cases, which is nothing but if it's an even number or if it's an odd number. That's the this is the most easiest way to do the rounding off part. Just remember this whole flow chart. Now let's discuss for each. If it's not 5, okay, then what do you do? If it's not 5, and let's say the numbers are greater than 5, which means 6, 7, 8, and 9, what you do? You add 1 to the left digit, then kill and go. Let me give you an example 4.7839, and I want to kill this number 9 greater than 5. So add 1 here. So 4.784, then you can kill this 9. That's how you change. Similarly, if it's less than 5, just kill and go, which means 1, 2, 3, 4, 0 also included. Just kill and go, which means that you can just remove it off easily. Let's say same 4.783, and I want to remove this part. Maybe let's add some 7, 6. So I want only two decimal places. So this you will remove, which means that 3 is removed, which means it's less than 5. So you can just kill and go. So the answer would be 4.78. Now, coming to a 5. If there is a 5, let's say 4.7605, and you want to kill this 5, and there is a 0 in front, what do? You look at the left. If you see a 0, you can just kill and go. So it's 4.760. If it's a non-zero, if it's even or odd, let's say it's one, the even, right? So it's 2, 4, 6, 8, and so forth. If it's odd numbers. For odd numbers, for the left digit, let's say 4.76, odd number 15, what you do is for you want to remove 5, and you see to the left of it, it's an odd number. So you add 1, then kill and go. So plus 1 to left digit, then kill and go, which is your answer would be 4.76, and 1 you'll add 1, so 4.762. Then you can kill the 5 and go. You get it? Now, for even, leave it as it is. Just kill and go. 4.7625. 5 you can just kill and go. So your final answer will be 4.762. That's it. Right. So this is the whole of rounding off just completed very simply. I mean, and for even this, just to give you some examples, just coming back on this, for all orphan rule, let's say 4.7003005. How many significant figures are there? First, going with rule number one, non-zero digits counted off. Non-zero, yes. Non-zero, yes. Three non-zero, yes. Five non-zero, yes. Two non-zero, yes. Now, specifically look at the zeros. What does this orphan rule say is that, let's say you have this, I think you can see, you have this zero over here. You have the zero over here. You have the zero over here. You have the zero over here. Look at the left of the zero. Do you have any non-zero? Do you have any person to support it? If yes, then you can count the zero. If no, I'm sorry, you have to kill it. So look at this zero. This zero has nobody on its left to support. So kill this zero. Oh no. Now look at this zero. This zero has somebody on this left to support. So count this zero. Look at this zero. This zero doesn't have any other person to support it. There's only a zero. So don't count this. Cut this off. And look at this zero. This zero has somebody to support it. Yes, please count it. So how many we have? 4703052. So 1, 2, 3, 4, 5, 6, 7. So 7 are the significant figures for this. Zeros at the end. 4.760000, whatever. They're just comedy pieces. Don't need to count them. 476 non-zero, 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 count it. Let's say you get this case 4.7006000. So these are not counted. This is counted, this is counted, this is counted. Now we apply orphan rule here. 0, but there's nobody to support, which means you can remove it off happily. But this 0 has 7 to support it, so you count this. So the number of significant figures is 4, and for this is 3. Even for non-decimal number, 470. Zeros at the end, kill it. 47. So we have only 2. A number with a unit, count everything. Don't leave. And numbers, just definite numbers like pi, e, and so forth. They have infinite amount of digits, which are significant figures. So the answer is infinity. Right. That's the whole story about significant figures and rounding off. Now coming to error analysis. Error analysis is a very easy topic. Not much there, but still you just need to know certain things. The first is about, let me give you a small example to prove my point. Okay, I have here a rod with me, and I know what is the exact measurement of this rod. Now I give you a scale to measure 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 1, 2, 3, and so forth. It's a, let's say it's an Natraj scale or something like that, right? So I give you the scale, and when you try to measure it, you might get three kind of outcomes. Number one, number two, and number three. The number one would be you got a exact outcome, exact number like 3, 4, something like that. Let's actually keep the thing as, let's say you got it as 3 centimeter. Well, good. You got an exact outcome, so you don't need to be worried about any errors in that. And what if I told you that the exact length is actually 3 centimeters? You'd be happy because what I've told and what you've measured is correct. Or it could be with a decimal, maybe 3.1, right? Or 3.2 or 3.3, something like that. Which means that uh, although it's the exact outcome, there is still a decimal point of uncertainty which you'd be measuring upon where you see it. And there's something called parallax error that you need to focus straight on to the measurement, not towards tilting to the left or the right, or you would get inaccurate results. Or it could be of it lies between 3.1 and 3.2. So in this case, you're not sure. Even in this case, you're not sure if it's correct or not. There's a decimal point difference. Here the difference is zero point 0.1 and here the difference is 0.01. So you're not sure. So what do you think? Is it your fault or whose fault is this that these errors are creeping in? Well, it is because of the instrument that you have chosen. It's called instrumental errors. There are actually three kind of errors: random errors, personal errors, and least count errors. Let me just write it for you: random, personal, and least count. Random errors caused by anything, various disturbances, and even the environment conditions and so forth. Personal errors, maybe you are biased to get such a certain reading, or maybe you have it's your mistake of you haven't properly calibrated the device or you're properly improperly measured, or you didn't know how to measure it properly. Least count errors are the errors like instrumental errors which you'd be facing, because the least count is nothing but the smallest value that you can measure with a certain device. What do you mean by that? Let me explain. Look at the scale. You have markings from 1 to 10 on a scale, which represents 1 millimeter. Each marking represents 1 millimeter. So, what is the minimum that you can do? What is the minimum measurement of length that you can do with this? A millimeter is what is the least measurement you can do. Can you measure 0.1 millimeter for me if I ask you to do? No, you'd say no, because the least is only 1 millimeter and I cannot go further beyond that, right? And so for this scale, the least count is 1 millimeter. But there are certain devices that people have invented so that you can measure even these small measurements also. Maybe it is just like necessity is the mother of invention. Some people would have thought, oh, I need to measure some devices or some things which are very, very small to handle. And if I really measure them, I can make best use of them. So they would have designed devices to measure some other of their discoveries or whatever it is. And we say happy birthday to screw gauge and vernier caliper. First came vernier caliper, then came screw gauge. And its least count is nothing but zero point 0.1 millimeter. And for this Maybe some people thought that, can I go more than 0.1 millimeter? Yes, you can go. This can measure 0.01 millimeter. This will be handled in the next section. And this error analysis, we have some terms to be defined in error analysis, like ways to express an error. There are three ways. Uh, One is absolute error. This also has mean error. Then you have absolute mean or mean absolute. Then the second one is relative error. Then third one is percentage error. Percentage error is nothing but relative into 100. Nothing. It's just this one, right? So now we actually have a format where you can express your errors in. The simple format is A plus or minus delta A. A tells you the true value, and delta A actually tells you to where the extent of error is, or this tells you about the error. And we also have, you know, uh, operations on this. Addition and subtraction will follow one operation or methodology. Multiplication and division will follow one methodology. For example, I'll give you the methodologies here, give you an example and do it. Let's say you have 7 plus or minus 0.3, and you have 4 plus or minus 0.1, right? So they'll give you these two. Maybe these are the length and the breadth of a certain, uh, maybe a object or something like that. They'll ask you to add or subtract it and tell me the final answer. So for adding or subtracting, let's see it for adding. For adding, what you're supposed to do is just add them up. Just add them. No need to worry about anything. 7 plus 4 is 11, plus or minus 0.3 plus 0.1. And also remember, errors are always to be added up, irrespective if it's a addition or a subtraction. It's just like, let's say you and me are students in class, and we have both committed a mistake, right? Although they are independent mistakes, the teacher finds out and asks us to both go out. Does he be like, oh, you have committed a bigger mistake than me, so he will not go out, which means I will not go out and you will only go out? No, the teacher would be like, both of you have committed a mistake, so both of you deserve to go out. Similarly, like that, errors, even if it's for subtraction, add them up. So 0.3 plus 0.1 is nothing but 0.4. This is a case of addition. But for subtraction, it is 7 minus 4. These absolute ones, which means that, I'm sorry for confusing it with absolute error. These are absolute digits. These are the, let's say, those are heroes. These heroes are supposed to be done according to the operation which is given unto them. Similarly, if it's for multiplying, you multiply them. If it's divide, you divide them. These heroes are to follow the rules of arithmetic operation. So if it's subtraction, subtract them. 7 minus 4 is 3. Plus or minus, but errors always you add them up, no matter what. But for multiplication and division, there's a bit different format. What you do is that you write it in terms of relative error. Relative. What do you mean by relative? A relative is a person who comes to your home. They start comparing you with somebody, that, see, this person has got better marks than you. See, this person has bought a land. See, this person has bought a car, a bungalow, and you are still sitting here and doing nothing. So they compare you with something that is better than you. It's like being compared with something. It's like a ratio that's being made of how much percent are you of them. Similarly, relative, it's like a ratio. So what do, you write the error on top, just as they feel that you are the error and there is a perfect person better than you. So the error is to be written on top. Over here, let's say for multiplication and division, the formats are same, but the operations that you do with the heroes are different. Well, which means if it's multiplying, you multiply. If it's divide, you divide. Which is write the format. The format, nothing is like, it's just like the one who's being compared, 0.3. 2, who is the best person, is 7. You add them. 0.1, who's the error, and 4, which is the correct, I mean the absolute one, then equal to. Now you form according to the sign. If it's multiplication, what do you do? 7 into 4 is 28. Then you leave this column as x so that you find out this x and you can write this as 28 plus or minus x in this format. Similarly for division, 0.3 by 7, the mistake divided by the original plus mistake 0.1 divided by the original 1 equals, what is, now we apply division. So 7 divided by 4, maybe it'll come around like 1.3, let's take, and this you leave it as x, so you get it as 1.3 plus or minus x. That's going to be your final answer. For these you got as your final answer. It's straightforward, but this is how you solved this one, right? This is for the formats. And also note, let's say you got it as addition, subtraction, multiplication, division. What about powers, right? Let's take, you got it as, the questions usually will be like, maybe a equals b cube. Now express it in a relative error, right? So how, what do? Just write, it's relative. A maybe as a plus or minus delta a, and b is nothing as b plus or minus delta b. So this will be given in the question, and now you are supposed to write it in a relative error format. So what you do is that you write the error by the original equals, you bring the power down. So 3 into error by original. This is the relative form of it. And percentage, just multiply by 100 on both sides. You'll get percentage. This is also very important. This also comes in a lot of MCQs and even some questions. But now I never told you how this format actually came in. Now let me tell that. So it all starts with mean error. So how are these errors identified? What they tell you in the questions, they give you 5 or 6 values or 3 to 4 values and so forth with the decimal places, right? And what you do is that, let's take this as A1, A2, A3, A4, or keep it as A5. So there are 5 values given to you. So what you do is you come stepwise. First, you do the absolute error part. Mean error. What do you mean by mean? Just take the average. So what do? So a mean is nothing but A1 plus A2 plus A3 plus A4 plus A5 divided by the number of items you have. Let's keep the number as n so that it will be simple. So you have till n terms. So divided by n. So this is a mean value. So you get a mean value, a mean. Now, what do you do with this? This is step 1. Step 2, to find out that error, that delta A part that we saw here, what do? You take the modulus of A mean minus an, which means that you put n equals 1, 2, 3, 4, 5, and so forth, and you get each and every value. Let's say you put a n equals 1. So a mean minus a1. Take the mod of it, which means that even if it's a negative value, write it as positive. So you get usually the numbers after the decimal. You get that 0 point something or with the decimal place. Then what you do in step 3 is that you got it till 5, 1, 2, 3, 4, 5, and don't worry, when we do a lot of problems, you'll get to know how this method exactly works, which I'll tell you. So just listen to these steps right for now, and then when we do the problems, we'll work it out very easily. So after you get those 5 decimal places, right, what you do is you again mean them, and that's actually called absolute. This is the absolute, this is the final error that we're going to work upon just to eliminate this error. So what do? You take mean of this. So this 1, 2, 3, 4, 5, you put it here divided by number of uh, items that are there. So this is that delta A part, right? And what is A? This is the mean is the A. That's the closest to the truest value that you can get. So A and delta A we got, and now happily we can form this format if it's being asked, right? Then about relative error, I already told you, which is nothing but the mean absolute error to the mean value of the quantity. This is actually called the mean absolute error. Mean absolute delta A by A. That's what is actually called the relative, right? And finally, coming to the most awaited part of the chapter, vernier caliper and screw gauge. Very, very important part. I'll summarize everything in a table instead of writing uh, a lot of key points. We'll keep it as vernier caliper, screw gauge. What are these instruments actually? Even you can look up in textbooks. Apologies for my drawing. The vernier caliper looks like this and also has another shaft running. Right. Basically, these are called jaws of the vernier caliper. These are the jaws, and you put an object over here. This is just a model. Screw gauge is nothing but like this. This is actually called the pitch scale or the main scale, and also over here, this is called the main scale. This is called the vernier scale, right? Even you can look at videos just to see how it actually is and how it works. But for solving numerical problems, you don't need that much. Just need to know just the formulas and how it works. This is the circular scale, right, with readings, and this is very minute. This is a circular scale, and there is something called the ratchet here, which you will twist and turn to get the readings. I mean, to exactly fit the object over here and to get the readings. So what is the least count of this device? The minimum that it can measure. Let's say my value actually came between 3.1 and 3.2 in this case. So I'd be a bit sad. I cannot get the exact. So don't worry. We have the vernier calipers for it. The least count of this is 0.1 millimeter. What about this screw gauge? Okay, let me say that I want another extra digit, but I don't know where to go, and this vernier caliper is not doing my job. Well, let's go for a screw gauge. That's more. precise. And mainly, these two are for the precision part. You get it? And there are things like accuracy and precision that I told you before. Accuracy is nothing but closest to the true value. Precision, more number of decimal places. And it's not like you can say every accurate measurement is a precise one and a precise measurement is always accurate. May or may not be, depending upon what situation is this. And for the formulas to solve numericals, just this formula for this vernier caliper, least count is nothing but one main scale division minus one vernier scale division. You might ask, what are all the kind of questions that you might get in this? Let me tell you. What they do is they give you this question like, let's say 9 vernier scale division equals 10 main scale division. So what then, what are you supposed to do? You find out the least count. They ask you to find out the least count. So what do? You try to substitute this input into the given thing. And they'll also give you the least count of the main scale. That will be usually 1 millimeter or 0.1 centimeter. Usually, they would provide it to you in the question. So how do you solve this? So what you do is, if 9 VSD equals 10 MSD, then how much is 1 VSD? It's just like asking, you have 10 toffees with you and you say it costs 100 rupees when you buy them. So if 10 toffees cost you 100 rupees, then how much does one toffee cost you? 10 rupees. Similarly, 9 VSD, if it's equal to 10 MSD, then it means that 1 VSD is nothing but 10 by 9 MSD. You get it? Or usually they don't give it to you in this way. Always the value of MSD is less than that of VSD, the divisions. So it's 9 by 10, because if it's 10 by 9, then you'll get a negative value of least count, right? Just for that. And so now you just substitute in the value. So LC equals 1 MSD minus 1 VSD is nothing but 9 by 10 MSD. MSD, you can just take it out. So 1 minus 9 by 10, which is 10 minus 9, which is 1 by 10 MSD. What is this MSD? They'll give you the least count of the MSD, which is nothing but 1 centimeter. So 1 by 10 centimeter, which is nothing but 0.1 centimeter, which is nothing but 0.01 millimeter. Usually you don't get least count in this fashion because least count of this screw gauge is 0.01. So it's just a example problem. Just don't take this as the actual problem. Well, when we see actual problems, you will get to know what they actually ask. And for this, least count is nothing but pitch divided by number of circular scale divisions. This is a circular scale. This is the pitch scale, right? And pitch scale, you would be measured 0, 1, and usually you get it as 0.51 and so forth. 0.51, and this is in centimeter. And these are just divisions, just for how much does this ratchet turn. And so this is everything about screw gauge and vernier caliper, right? So this is the complete chapter of vernier caliper and screw gauge. So thanks for being with me till this time. Do see you in the next session where we come up with a lot of numericals just to solve them for you. And definitely I will try to post all this in my Telegram channel, which you can have it in the description. You can join me over there. And if you have any other doubts, any other things that I said wrong over here, please do feel free to raise your queries, to ask your doubts. Mail me at academiawellexplained@gmail.com. If any other ambiguity, Do put it in the comment box. I will try to respond to it as soon as possible. Thank you.